So for this question, it states, let x be a set and have a distance metric d, x by x, go to the set 0 to infinity. So for parts A through D in this question, it's basically asking for certain examples of a space as well as a distance metric, which fails and passes parts of the metric space axioms. So let's call the metric space axioms as such. So for part A, it says, give an example of a pair, space X and metric D, which obeys axioms B, C, D, but not A. So the distance metric in this hint is given as such right here. So let's modify it to look like this. And as you can see, part A fails because this is 0.5 when it's itself, and yeah, it fails. And parts B and C passes. Part D is a little more tricky. We have to split it into cases. X equals Z is trivially true, right? As we see like right here. And when case is not equal to Z, we can just basically split it up right here, and kind of see that, okay, if this is equal to 1, that implies that this is equal to 0.5. That implies that this is equal to 1 as well, right? So it would be basically be equal to 1 is less than or equal to 1.5 because you're adding both of these right here. Keep in mind, this is without loss of generality. You can apply this to all sorts of cases, right? So let's go to the cases where x is not equal to y and z is not equal to y, right? So this is just the equality case, which is just 0.5, 0.5, which is 1, which is less than or equal to 0.5. Therefore, D is satisfied. So for part B, it says, give an example of a pair, space X and metric D, which obeys axioms A, C, D. So let's define the metric right here, space X equal to the set of real numbers. This metrics is going to be a piecewise function such that X is equal to Y is equal to 0. And when X is not equal to Y, it's going to be absolute value X minus Y minus 1 right here. So part A is trivially true. Part B, axiom B. You can clearly see that if you plug this into the formula right here, you would not get 0, which breaks part B. Part C is pretty trivial for x equals y case and x not equal to y. This is always true because you're just swapping them right here by using the absolute value, factoring out the negative 1. Axiom D, very similar. You can use triangle inequality, which I proved in the last question, to prove it is true. So for part C, give an example of a pair with set X and the metric D, which obeys axioms A, B, D, but not C. So let's define this space right here, X equaling to the set of real numbers, and this metric equaling to X minus Y, negative 2 times X minus Y, such that this is true when X minus Y is greater or equal to 0, X minus Y is less than 0. And so this is very similar to the absolute value case, except for this negative 2 value. If we just remove the 2 from here, it would equal the absolute value case. So part A is pretty similar, trivially true. It's the same thing right here. It's equality right here. And then so for bringing up the cases for part B, such that since x is not equal to y, let y equal to x plus c, and so we just factor them out and see we can get these two things. Keep in mind that for this one, c is less than 0, and multiplying a negative number by a negative number against a positive number, so therefore this would be greater than 0, such that c is not equal to 0. For axiom C, the distance metric is equal to 1 right here. Distance metric is equal to 0, 1, negative 2 is equal to negative 2 times 0 minus 1 equals to 2, which implies that this is just not true. C fails. And part D, trivially true using the triangle inequality. Very similar. We just put it into cases, but for this one, we just factor out the 2, and we can see that they're equal, very similar towards what I proved in the last video for triangle inequality. So for part D, it says, give an example of a pair, space X and metric D, which obeys axioms A, B, C, but not D. So this one was a bit more difficult, but this is what I came up with. Let X equal to the positive set of real numbers. You technically apply the absolute value of both of these and just say this is the set of real numbers, but out of laziness, I just didn't do that. To with negative cases for axioms B, I think. But yeah, axiom A is trivially true because we find it to be such. Axiom B, just without loss of generality, we can just apply both cases and see that these are always positive for these cases. So this basically avoids that when there's a 0 there, we pick the maximum. And we know exclusively that another one is not 0 here. So this will always be positive since this is a set of all positive real numbers. And the minimum here, well, it's going to be a minimum of 2 numbers that are first of all positive and also not equal to 0. So therefore, trivially, you can see that this is always greater than 0. Axiom C can trivially be checked to be true by just swapping them. It's all different cases. But I think interesting for axiom D, right? Let's do D of 5, 10 is equal to the minimum of 5, 10, right? D of 5, 1 is equal to 1, and D of 1, 10 is equal to 1. Well, as you clearly see here, the triangle equality doesn't fail, or the triangle equality isn't true here, so axiom D fails.